Okay, so this is lecture 4 and we are discussing existence of the solution, existence and uniqueness of the solution. So in this context we have understood what is uniform convergence of sequence of function. Okay, and then now let us just very quickly look at something called Lipschitz function. Okay, so Lipschitz function, a function f is said to be Lipschitz at a point x0 if there exists a neighborhood means open interval, or in 2 dimension it means that some rectangle without its bound. Okay, there exists a neighborhood of x0 such that given okay, I don't need epsilon thing, such that for all x in that neighborhood there exists L such that fx minus fx naught is less than equal to L x minus x naught. Okay, so note that this L can depend on x, and that's why in this case it's called locally Lipschitz. Locally Lipschitz at x naught. So it's called locally Lipschitz at x naught. Now there is generalization of this definition. So for example, we can generalize this definition to a domain, and in that case this L will not depend on this. Sorry, I had to change the definition a little bit because I made a mistake, such that for all x1 comma x2, I made a mistake. So all x1 comma x2 in that neighborhood, x1 minus x2 is something like this. Okay. So it's not only x0, but in that neighborhood for all these point intervals. So we can extend it to a domain. So a function f is said to be Lipschitz continuous. Now this is not a locally Lipschitz thing, it's a Lipschitz continuous on a domain on omega, and this definition will be more useful for us if there exist L positive numbers such that fx1 minus fx2 is strictly less than x1 minus x, or less than equal to x1 minus x2 for all x1 comma x2 in this domain omega. Okay, so let's say f is omega to r. So we'll use this, but one can use this also in some cases. Okay, note that this neighborhood can be very small neighborhood. Okay, and because it's a small neighborhood, that's why this L depend on this x. So some function might be locally Lipschitz, they might not be Lipschitz. Now there is another version of this definition which says about globally Lipschitz. That means the function is Lipschitz for whole its domain. Now here I'm looking at the Lipschitz continuity in the domain omega, but in general, if your function is defined, let's say on R, then it will be globally Lipschitz if this L is independent of X. Okay, so these terms globally Lipschitz and locally Lipschitz, one has to pay some attention. All right, so now once this is clear, and I assume that this was clear to you in the first year OD course also, we'll try to prove the theorem which I stated last time. Did I state that theorem last time? Okay, yeah, I stated this thing. So this is the statement of the theorem, is that let T naught x naught be a interior point of the omega. Now omega is subset of R2 here, where f is defined, and f is locally Lipschitz with respect to x. Now you can see this word locally came. Then in that in a neighborhood of x naught. So this is what I mean by locally Lipschitz. So locally Lipschitz in the neighborhood of T naught x naught. That means it's locally Lipschitz at T naught x naught. Then the Cauchy problem has unique solution defined on a suitable neighborhood. Okay. So now we have to find this suitable. What do you mean by this word suitable? This will be highlighted, and this will be governed by this locally part. First we have to identify the domain where function is locally Lipschitz. That means this whole, and then we have to use that domain to go further. Okay, so let us try to prove this statement. Now here note that f is from omega to R, and f has two elements, basically t and x. I don't know what order I am writing them currently. Let me just go back. Okay, so I'm writing them in the order of, let's see what order I'm writing so that I can just keep writing in that order. First I'm writing t, or okay, first I'm writing t. Okay. All right, so this is fine. So that means the first, so this is a subset of R2. So the first element, so we have to take t naught comma x naught. I'm writing in this form. And when we say a locally Lipschitz of f with respect to x variable, this implies that there exists a rectangle around t naught comma x naught, sorry, okay, in omega, such that f of t comma x1 minus f of t comma x2. Now note that the locally Lipschitz is only with respect to the second variable. This is less than equal to L x1 minus x2 for all t comma x1 t comma x2 in that rectangle R. Okay, so we'll denote this rectangle by this R. Okay, so one thing you should note that this L, of course, it will depend on t naught and x naught, but this is independent of t. So it will only change if you change this t naught. So for all other t's in this domain, this will be independent. Okay, in general, this is independent of t because this you see that this will hold for all t, and of course it will be independent of x and x2, but it will depend normally on x naught. So if we shift the domain, local Lipschitz thing will be changing. Okay. Now, once that is clear, so we have generalized this definition to the 2D test, 2D case. So now let us look at what is R. So R is a rectangle, and the rectangle will be denoted is basically a set something like this. Okay. Okay, so this should be B and this should be A. And you can see that this is without boundary, because there has to be open sets. Okay, so in general it is the case, and you don't have to take the boundary. If you want, in this our case, you can take the boundary, and then this has to hold for even for the points on the boundary. That is because the okay, so once you have the open rectangle, you can just take a smaller rectangle, where you have to take the bound. You can take the bound. So for our case, it won't be much difference if you take either of that, but let's take the boundary, so then the life is easy. I will point out when the boundary plays any role. Normally it doesn't. All right. So now for the first thing we need is that M, because we know that F is a bounded function. Okay, and R is basically subset of omega, and F is bounded on omega. So what we'll have is that we'll define a number M, which is nothing but M, basically maximum or more of Fx over R. So this is independent of whether R is open or closed, because M is a bound over whole omega. So it will, this bound, the same bound will also make sure that this is the case. So this M will always exist. In particular, we take this over this R only. Okay, and then we define a number H, which is basically minimum of A comma B by M. Okay, and this is an important number. I will explain in the second why this is an important number. And for this H, you see that in the theorem I have not mentioned what is the neighborhood, right? I'm saying suitable neighborhood. So now I mentioned the suitable neighborhood. So this H gives the suitable neighborhood, and so that we will say now that the solution will exist, and we will prove that also for t minus t naught less than equal to H. Okay, so solution will exist in neighborhood of t naught, and X will be allowed to go as only restriction we have is on this t. So there is no restriction on X. X can go as long as it stays in R. As long as it stays in R, t can move here. So now let us try to understand this setting. Okay. So there are two different things we have to see. And this picture you might have seen before also. Okay, so I'll draw another box. Okay, so now let's assume the center of this point is t naught x naught. Center of this box is x naught t naught, and then you can see that, so this is t direction, this is x direction. Okay, so this will be b, and this distance will be a. Okay, so now similarly here, this is t naught x naught, and all the things are exactly like this. This is a, this is b. Now we'll, through the point t naught comma x naught, we will draw a line. We'll draw two lines actually, but so let's write, draw lines with slope slopes m and minus m. What is this m? This m is a bound on this f. So I should be careful. This is depend on t comma x, right? So I should change this and I should write it t comma x. Okay, so there are two possibilities. In one possibility is that these lines go something like this. Okay, that means they if you look at these points and draw these lines again. So these points are, so basically the distance where this line intersect the boundary x is equal to b, x naught minus b, is less than t naught minus a. So basically what it means is that, note that these slope represent a bound on what? They represent on the bound on the slope of x prime, x. So x prime is the derivative, so it's a bound on x prime. So that means x cannot grow faster than these slopes ever. So what it says is that basically the characteristic, the line or the solution line will always be somewhere here. Okay. Now problem is that if this happens, so if this distance is there, that means if this line intersect our upper and lower part, then this can go out from here, and we don't want that. Similarly, this can go out here. Of course it might not go here through this one. It might just go here also. There is no issue. But the only information from what we have and from which we can conclude is that if you look at this box, then the point t comma xt will always stay inside R. Okay, and we have locally Lipschitz function only in f, so we don't want to go outside this. So we'll choose this box, and in this case you will see that h will be equal to b by m. Okay, so this length is basically b by m. All right. In the other case, life is little bit easier, because what happens is that, okay, if you see that these lines are behaving like this. Okay, so I'm trying to get a proper line. Okay, so in that case, if you look at the way the trajectory will behave, they will always be in R. They won't be going outside. They won't be hitting the upper boundary. They won't hit, right? They will always be here. So in this case, that is the second case, what we'll have is that h will be equal to a itself. So that's why we have. So in this case, we will have complete R. So this box. So the trajectory will always be in this box R. Here the trajectory will be in the smaller box, and this box is given like this. So that's why this number h is defined. Where is h? Okay. Now this is an intuition. I'll prove that. Now what I draw is not a proof. It's just to tell you that how things will behave. Now I'll try to prove this. So let us try to prove these statements one by one. Okay, first is a claim which we already proved. Basically, it says that the x prime is equal to f t comma x, x t naught is equal to x naught on, let's say, R except the boundary. Because we cannot define the derivative on the boundary. It will be, if you can define it, will be one-sided derivative. And so this is equivalent of saying that you have xt equal to x naught plus t naught t f t x, sorry, not t, s x of s ds for all t minus t naught less than equal to h. Okay, and this we already proved. Right, by fundamental theorem of calculus. The second claim is more interesting. Now we define sequence of functions, a sequence of Picard iterations. Okay, basically we'll say x naught t is equal to x0. So this is a constant. The first is always constant. The second one and the further one might not be constant. In general, they are not constant. This is t naught to t f s x k s ds. So this will be for k is equal to 0, 1, 2, and so on and so forth. Now claim is that these x k plus 1 t for k is equal to 0, this, okay, are well defined and the domain of this trajectory, that means t comma xkt, such that t minus t naught is less than equal to h is always a subset of R. So this is exactly what I mean when I say that if you enforce this h thing here, then either this will happen or this will happen. In either case, this trajectory will always be in R. By choosing this h, we are making sure. Okay, so now let us prove that. What I need to prove to show the trajectory is, so this is a claim. So proof of this claim, so that was claim 1, let's call it claim 2. Okay, so let's just try to prove this claim. What I need to prove? I need to prove that xkt minus x naught is less than equal to b for all t minus t naught less than equal to h. Okay, that's all I need to prove, and that is visually actually harder to see. So you have to make these two cases, but if you start writing the proof, it's actually trivial, because not that this part is equal to integral t naught to t modulus f s comma x k minus 1 s, okay, dx, sorry, ds. Okay, this is less than equal to integral t naught to t f s x k minus 1 s ds. Okay, now if xk minus this is in R, then this is bounded by M. So we have to argue iteratively. For k equal to 1, this will be x0, and that is inside the domain, inside R, so this is bounded by M. Similarly, so once for you got x1, then you go to x2 and so on and so forth. So you can argue basically by induction. But this, so if you assume that this is in R, then this will be less than equal to m t minus t naught, okay, which is less than equal to b, because this is nothing but h, okay, and h is always, m into h is always less than b, either because h is either a or this. If it's a, then that means anyway a is less than b by m. So this will always hold. So the proof is easier compared to what you see geometry. Now this means what we have proved. This means all the trajectory, all these t comma xkt are in this rectangle R and well defined. Well defined is anyway trivial, right? Because the Picard iterations are well defined, because you know this is a constant, so this integral is well defined, f is well defined, and you are making sure that the domains are this t and these things are always inside the R, and all these integrals are bounded anyway, right? This also shows that these integrals are bounded, so this will be bounded. So everything is well defined. Okay. Now what we need to prove? Now what we are going to prove, and this is the main claim for today's class and for this theorem, is that we want to prove is that the sequence xkt, this is now not that there is a sequence of function. We are going to prove that this is uniformly Cauchy sequence. Okay, so once it's uniformly Cauchy, it will converge uniformly and then we are done, right? So it will converge to some x and then we will be done. Okay, so now how would we prove that this is uniformly Cauchy? So note that what we need to prove. We need to prove that maximum, and this is to prove maximum of t, let's say t naught less than h, xm t minus xn t is less than epsilon for all n comma m bigger than some capital N. Okay, so given epsilon positive, there exists capital N such that this holds, right? This is what we said was uniformly Cauchy means in the class before this class. Now what we'll do to prove this such an estimate is that we will prove our estimate to measure the distance between xk and xk minus 1. Okay, and when you go from m to n, we'll see whether m is bigger or n is bigger, and then we use these telescopic sum to basically get estimate over this kind of thing. So let us try to get an estimate over this kind of term. Okay, so in that direction the claim is the following. So again, this is a smaller claim. We want to prove is that this is less than equal to m by L t minus t naught power k L power k by k factorial. And if it doesn't make sense to you what is this bound, it will come in a second. Okay, it will come once the proof is over. Okay. For all t, okay, so this depends on t, so for all t naught minus h to t naught plus h, and because it's a closed and bounded set, so this can be made independent also, independent of t also. But let's not go there. First, let's try to prove this thing. So clearly, let's measure the distance between x1 and x0. So we'll do by induction. So note that x1 minus x naught is nothing but integral of t naught to t f s x naught is a constant, and ds. Okay, so this is less than equal to m t minus t naught. Okay, the modulus sign so the modulus sign came because because if the t naught is t is less than t naught, then we have to take the other way around, but because everything is absolute, so the modulus sign will come. So now similarly we can do it for x2 minus x1. Not that in this case k is equal to 1, right? So basically this L get cancelled with this L, and this remains. Okay, so only this will remain. Now let's look at x2 minus x1, because that was a trivial situation. So in this case this will be equal to integral t naught t f s x1 s ds minus integral t naught to t f s x naught ds. This is less than equal to integral, you take modulus sign inside, this will be t naught to t f of s x1 s minus f of t f of s x naught s, okay, ds. This is less than equal to, now you use the locally Lipschitz because everything is in R, so it makes sense. So this will be L. Note that L is independent of S, so it's also independent of T because T is in R. So this will be T naught to T x1 S minus x naught S ds. But for that you know the bound. So only thing is that T will be replaced with S. So this will be less than equal to L t naught to t. This will be, now s m will come out, s minus t naught ds. Okay, and once you do this integral, which is trivial, whether you divide into two parts, either way there get only two, there are only two cases. One t is less than t naught, another one is t is bigger than t naught. Whichever you choose, you will get the same answer. This is m by L, and basically you'll get t minus t naught square by 2. So this is something like t, so t square by 2 is the answer. Okay, so now by induction you can do the same thing. You assume it's true for k minus 1, and we want to prove for k case. Okay, so we assume for that is true for k minus 1, and then we want to basically we are saying that it's true for all the so here k minus 1 is this. Okay, so that means we are assuming that for xk minus 1 this will hold. Okay, then we will go look for the estimate on xk plus 1 minus xk. So of course this is with respect to t. Repeat the same thing. Once you repeat the same thing, what you get? So let's do it anyway, so that we are on the same page. this is equal to, but I'll do it a little bit faster now. So integral t naught to t mod of f s x ks minus f s xk minus s ds. Okay, yes, ds. This is less than L t naught to t. So you can see that every time one L come out. Okay, and then what is left inside is xk s minus xk minus 1s ds. This is less than equal to L t naught to t. Now here we'll substitute the expression for this bound like we did here. So we do the same thing. So here the expression will be m by L. Okay, so what was the estimate for that? It will be m by L, because now instead of t it's s, so s minus t naught power k L power k factorial. Okay, so this is the estimate. Now you can take all the constants out, so this will be equal to L. This L get cancelled with this, so you don't want to cancel it because we want to preserve the structure. So this L will be put together with this thing, so you get Lk plus 1. Okay, and then you get multiply with m divided by L, and then k factorial comes out. Okay, so this is this L, this k factorial is this one, and this L combines with this one, and m is here. So what is left is integral t naught to t s minus t naught power k ds, and this is equal to m by L k plus 1 k factorial. This will be basically nothing but t minus t naught k plus 1 divided by k plus 1. So now you can combine this in this. Okay, and then we get the desired result, m by L t minus t naught k plus 1 factorial L k plus 1 L power k plus 1, and this is exactly what we wanted to do. Okay, in particular, now let's look at this term carefully. So the claim 3 is the proof for the claim so the sub claim is true, so this holds now. Now we'll use this to get this thing. How would you do that? Because we are on R, and that means t naught t minus t naught is less than h. So what we can do is x k t minus x k minus 1 t, and if you take maximum over t minus t naught less than h, because this is what makes sure that everything is in R, and this is where we are, will be less than equal to m by L k plus 1 by k factorial, and this t minus t naught is bounded by h, so this will be hk. So this, sorry, because I wrote k and k minus 1, I don't write k plus 1, so I had to just write k only. Okay, so note that this bound is independent of t, which is a good thing. Okay, now to show that we are uniformly Gaussian, now we'll consider these terms, and write them in a telescopic. So assume that m is bigger than n, then you look at xmt minus xnt. Okay, this will be xmt minus xm minus 1t plus xm minus t, and you can keep writing it till xn plus 1t minus xnt. Okay, now this will be less than equal to xmt minus xm minus t xn plus 1t minus xnt. All right. Now each one of these individual term will have this bound. Only this index matters. Okay. So now you can take maximum both sides, maximum of t minus t naught less than h. Yeah, all the maximum will go here individual, and this inequality will still hold. And then you can sum them up. So what you will get is the following. You'll get here, so for example, for this case, you'll get m l power m factorial h power m. Okay, so similarly for the next term, you'll get capital M l m minus 1 m minus 1 factorial h m minus 1, and so on and so forth. Here in the last term, you'll get plus m by l n plus 1, okay, h n plus 1 by n plus 1 factorial. That's it. Okay, so we are almost done now. Why we are almost done? Let's look at this thing. I can write it in a little bit nicer form if you want. This is nothing but, you look at the so let's write this term. So this will be m by l k h k by k factorial. If I write summation in front of it, this is going to be equal to m by l exponential lh. Okay, so, and we know that because this is exponential, this series always converges. Right, because it's equal to exponential LH, and of course multiply by ML. So this means the partial sums of this series converge, right? And the partial sums are nothing but the sum of first n terms. So Sn will be equal to sum of Sn. So that means the Sn converges. And note that Sn is a sequence of real numbers. Okay, because Sn converges, and just somewhere I should write Sn is nothing but summation I is equal to 1 to n of m by l li h I factorial I. Okay, this implies that sequence Sn is Cauchy. This implies that given epsilon positive, there exists capital N. Note that every converging sequence is Cauchy sequence, and this is just, I'm talking about the normal sequence. There is no function here. Okay, because Once you fix h, this becomes a numbers. So that means there exists, given epsilon positive, there exists capital N such that Sn minus Sm is less than epsilon for all n comma m bigger than n. Okay. And what is Sn minus m? Exactly these terms. Okay. So this is nothing but this term, and this is they are just real numbers. So I can make them less than arbitrary epsilon. So that means I just choose this and basically just depend on this sequence Sn, which is nothing but a series, okay, which defines exponential series. So this implies given epsilon positive, there exists capital N such that xmt minus xnt maximum over t minus t naught less than equal to h is less than equal to Sn minus or Sm minus Sn. Now this is not that a constant series, so this will be less than equal to epsilon. So this implies that Xm is uniformly Gaussian. Okay, because this epsilon is independent of t. There is no dependence on t. It only depends on h, and we already taken h has nothing to do with the t. So this implies the sequence of functions xmt converge uniformly to some function xt. The Cauchy does not tell you what is the limit, but it tells you there is a limit. We are just looking at that limit. Once that limit is there, we are almost done. So now this finishes the proof of claim 3. Now the last part is that we are going to show, so we can write it as a claim 4 if you want, is that this xt, this function xt is the solution. Okay, how would you show that? You look at the Picard iteration, and pass to the limit. This we discussed before we discussed the uniformly convergence. Okay. So you take the limit both sides. All right. So this converges uniformly. So this will converge to xt. This first part is constant, so this can come out. Plus, because now there is still an issue, because we have shown that xk converges uniformly. We have to show actually that fxk converges uniformly. But that is fine, because note that f, if you look at the sequence f s x k s, because f is Lipschitz, this will also converge to f s x s like this. You have to use the Lipschitz of f, okay, because f is locally Lipschitz. So that means I can change the integration in the limit. So I can write it as a t naught to t. Please try to prove it, this part. Okay, this is easy, so not much is there. So this is limit k tending to infinity f s x k s ds, which is equal to x naught plus T naught to T Fs xk xs ds. So that means our integral equation is satisfied. So xt is the solution of our ODE by the claim 1. Okay, so this way we are able to prove the existence of the solution. Now what is left is some uniqueness arguments, and then we'll go forward and discuss whether this condition is sufficient, or all those things will be discussed. Okay, so clearly it's sufficient. We have to see that it's not necessary. Okay, and we'll discuss that. So for that, for today's class, I just stop here. Please go through it. It's very technical. It's not very technical, but it's some technical. But you should go through it once at least. Yeah. I stop here, so I'll stop the recording, and then I'll take your questions.